Hello, everyone. Thanks for joining today. I'm Jamie, and I want to welcome you to the Interface webinar today, Dimensions of Multi-Axis Sensors. This event is being broadcast to participants all over the world, so we want to thank you for joining the conversation. And today we have a few of our experts on hand to address some of the questions that we get about a growing technology and some of the use cases. So thanks again for joining. And just to give you an outline of what we'll be talking about today, our agenda is going to start with some of the introduction on features of multi-axis sensors and why people are choosing this type of sensor in test and measurement. We'll go over some of the product specifications and applications and use cases, address common FAQs that we get here at Interface, and then of course give an opportunity to answer any questions that you may have. As noted, when you enter into the conference, your meeting microphone will be off. However, if you do have a question, you can unmute yourself, or you can simply use the chat feature. Today we have presenters from Interface, Ken Bishop, who, as well as Brian Peters and Keith Skidmore, will be highlighting some of the different aspects of multi-axis sensors. So to kick things off, Brian, why don't you give it a start here?
All right. Well, thank you, Jamie, and thank you everybody for joining. We know time is of the essence here, so we'll try to get through this quickly, but we do have some time scheduled at the end for Q&A as well. So I thought I'd start off by kind of reviewing force and torque sensors in general. Those of you that are here obviously have some familiarity with those types of sensors. And as you know, most of these sensors are going to be bidirectional, right? So you'll have a signal output, positive, negative, usually for tension and compression, or clockwise and counterclockwise applied torque if it's a torque sensor. However, both of those signals are in the same axis of measurement. So other sensors can be had with second or third redundant bridges. Those are usually called dual or triple bridge sensors, and those will have basically duplicate bridges designed to measure the same axis of measurement. Those are used for maybe control loops or redundancy for data AC. However, those are still slightly different than what we're going to be talking about today. And those are multi-axis. So multi-axis will essentially have dedicated bridges to measure very specific loading directions. So a little bit different. Go ahead, Jamie. All right. So high level, what is a multi-axis sensor? Well, fundamentally, they share similar design and construction to most strain gauge based transducers, in that there's going to be Wheatstone bridges applied to various machined components within the sensor. Typically, it's referred to as a flexure. However, these are going to be designed and implemented so that, again, they respond very specifically to applied forces. And those forces could be many different directions. For example, a lot of our sensors are going to be axial torque or axial shear. Those are going to be some of our 2- and 3-axis sensors. So for axial torque, you'd be talking about the FZ along with the MZ torsional value. For axial shear, that would be an FZ with the FX and FY shear components. And then some models will handle all 6 degrees in terms of all 3 load axes as well as all 3 moment axes. They usually start life as one of 3 different configurations. You're going to see axial sensors that have additional bridges added, whether it be for torsional or for moment measurement. And as you can imagine, those are primarily going to have higher axial capacities for that particular channel. With the other ones being usually slightly lower in range. The next flavor would be a torsional load cell, where we add axial or other types of bridges, such as our 5600 there on the right. Again, you can understand that you might have a little bit lower tension capability, for example, from that sensor. In fact, in that case, we've highlighted there that that's a compression only. So that's something else to note, is that sometimes you end up with a situation where they're not fully bidirectional for the additional bridges. But the last type are going to be dedicated multi-axis designs. So these sensors start life with the intent of being a multi-axis, and you're going to find usually more balanced capacities for the different bridges. And then from there, you're going to have either discrete outputs for each axis, or you might have a situation which is common for 6-axis sensors, where you have various signals coming out, but they're not already, how do I put this? They're not discrete for the actual measurement axis. So I'll explain that in a little bit more detail here. So these are a couple of our 3A 3-axis sensors. So both of these are designed to measure FZ and FX and FY shear loads in addition to that axial. You can see on the left there where we've exposed some of the machined elements. You can almost imagine that being 3 load cells attached in a string with the load pad there in the center at the end of that string. So each load cell in that 3-axis sensor, or each flexure is aligned and will be gauged such that it responds to that particular load. The one on the right is a little different in that instead of it being all sequential, it's designed with more symmetry, where we have the the FX and FY shear bridges or flexures designed in such a manner that you have better symmetry and more consistent loading there. But again, this is where you would have 3 bridges where each bridge would provide a specific FZ, FX, FY, for example, signal output. Now here's a cutaway of our 6-axis sensor, which is similar to most of these types of sensors on the market. And these, you can see, are a little bit different in that we have essentially 6 bridges on the sensor. However, they're not aligned in any particular force orientation. So these sensors rely on detailed calibrations where through that calibration process, you establish a coefficient matrix, which can then be used to but adjust each channel output to determine what the discrete axis signal measurement is. So these are nice in that you end up with a guaranteed symmetric loading condition with high stiffness typically, and symmetric and low deflection to that. The only caveat here is that you do need to implement some math, which is typically done in the instrumentation, or we'll have to handle somewhere to be able to then interpret those 6 individual millivolt per volt signals.
Mark
is now exiting.
So one thing we wanted to accomplish today is to get you thinking about some of your existing testing or upcoming testing. It's usually pretty straightforward when you know you're going to need a multi-axis force or torque sensor to be able to handle a particular test. However, what we're finding is many of our customers are going back and taking a look at existing test applications and realizing they can gain quite a bit out of having the additional channel data. Oftentimes, you do your best to isolate load conditions, but the reality is you may have other forces transmitting through that particular test article. That can lead to a lot of complications, as you can imagine. So again, we're finding more and more that it does not hurt to take a second look at existing test and basically ask if you would get more insight through additional channels. Some of the advantages, you can essentially consolidate multiple sensors. Obviously, if you're using different types of sensors in a particular test article, maybe you can consolidate, save space, save mass by integrating everything into a particular sensor that has all channels built into it. You can measure and verify if there's any system level crosstalk in your test setup as well. Again, is there side loads you weren't aware of? Are you introducing bending moment that you weren't aware of? And for fatigue testing, that can play a big role in the actual service life of the article. You may have impacted test data essentially because the test maybe wasn't quite as pure as you thought it was from a force introduction standpoint. We're also finding many customers are looking at the reaction side of a test article. Typically, there were assumptions made historically in terms of you have your imparted forces to the test article, and you assume what's transferring through and what's coming through on the other side. Integrating multi-axis sensors allow you to verify that. So it improves your model verification as well as significantly improving the test data you obtain from each test, really. Given that these are sometimes used in what I would call hairier applications, whether it be from a load introduction standpoint or even geometrical standpoint, make sure that you look at a couple aspects such as what is going to be the actual force at the sensor face, and how does that correlate to what a sensor is rated for. So that would apply to safe overload, ultimate limits potentially if you've got a dynamic or something where you may have a potential dynamic event, and then also allowable moments. Most sensors are going to have that information. Most multi-axis sensors will provide, or you should expect to know, allowable moment values, for example, or torsional or overhung moments also, depending on the type of sensor, so that you can try to set up that test configuration to where not only do you ensure lowest error introduction, but you also ensure good sensor life. And obvious rule of thumb, look at whatever axis is most important to you and start there. Start with whatever that primary axis might be, and then look at supplementing with the additional bridges or additional force vectors that you're looking to get. So I'm gonna hand it over to Ken here. He's gonna talk a little bit about our products.
Hello, everyone. Yeah, I'm gonna take you through some of the product offerings that we have. And let's see, we'll move through two-axis, starting with our TXY product. Basically, this one here has a axis in the X and Y. So it usually can be measured lateral forces, measures lateral forces, may be installed sideways in an application so it's narrow and fits into compact areas. And let's move to our next one. So these are axial torsion type units. So we've got force in, let's say, the Z direction or torsion around that Z. One thing that's interesting about these type of products, there's a number of different ones I'll take you through, is that ones that are initially designed for force will have a higher output in, let's say, the force direction and lower output in the torsion, and vice versa. So just keep that in mind. And we'll show you right here some of the product. The AT101 has basically 5 different capacity combinations. It works, of course, in the force and torque directions, and the capacities are stated there. Same thing with AT102 and AT103. Those are flange styles, and they can do compression and torque. Now, when we look at the model 1216, that one is based on an interface low profile design. So you've got a flange mount, and then you can have the extraneous load resistance like interface low profile designs have. So that's one of the advantages there. And on the model 2816, now we're moving up into a higher capacity version of a flange style axial torsion load cell. And again, based on the interface low profile design, so it has the extraneous load resistance. The model 1516 has single capacity, and it's a flange style. The model 5600 is based on a torque transducer design. So again, we'll have the higher output in the torsion direction. And then in this case, as Brian stated earlier, only a compression direction with the torque. So the advantages of using these types of load cells is there's many capacities to choose from and a variety of different mounting options and sizes. So it gives you some versatility. Now we're moving to our 3-axis load cells. As Brian stated earlier, you've got a 3 load cell type design, but with a lot of symmetry in it. So you've got 3 full bridged outputs. So if you're used to working with, you know, a regular millivolt per volt load cell, you can basically operate each one of these bridges as a regular standalone output. It's a small size, and you can have an IP68 option, which is attractive. The 5200 series is basically has a force in the Z and then moments. So like a windshield wiper over the top of the load cell. And again, it's based on the interface low profile design. It's simple mounting, a single hole in the top, a single hole in the bottom, and you get thrust and moment measurements at the same time. Our 6-axis load cell, as Brian described earlier, is a product that has a coefficient matrix. So if you remember the beams that he showed you, we have 6 independent beams in there that are full bridged output beams, and the coefficient matrix basically coordinates the relationship between each axis and those beams, how they react to it. In some cases, in our lower capacity units, it's a 36-term matrix. On our higher capacity units, it's a 72-term matrix. So some of the advantages are that more data is better. And some of the things Keith will talk about will explain that more. But sometimes you learn a lot by seeing what happens in 6 different axes as opposed to, let's say, 3 or 1, things you didn't know. Accuracy. The product with the standard calibration is very good, let's say around a 1% system accuracy, but finer calibrations can be done specific to the application that you're doing, and so that can make it even more accurate. It's cost effective, and it's a very stiff product. So system solutions, we have the ability to take products like a axial torsion load cell and combine it with our SI-USB, that's a 2-channel USB interface module, and provide you with this scaled together to work right when you get it from the get-go. Our model BSC4D, same thing, it's a USB interface module. We can put that with our model 3AXX load cells and give you straight interface to your PC, giving you logging, graphing, configuration. The BX8 is our 8-channel data ACK, but it works perfectly with our 6-axis load cell. And what it does is it can do the coefficient, matrix coefficient math internally. And so this makes it a very easy way to work with the 6-axis load cell. It sounds very complicated on the onset, but when you get a BX8, basically it's point and click, load the matrix, and the matrix math is already calculated internally, and then provides scaled analog outputs for you to work with to your system. And then we also have some multi-channel bridge amplifiers, just in case you want to take it and do all these calculations or inside your own data ACK. Our model INF4 will give you digital outputs, and our model BSC4A can give you analog. And these are, like I say, multi-channel up to 4 channels. So why interface instrumentation? Well, one thing is that there's a lot of instruments to choose from. And so interface can help you pick the right instrument that'll go with the product that you're using, the multi-axis product you're using. And then we can also take it to the next level, and we can scale them together and give you a cert if you need it. We can help you with options like TEDs. So that'll help you have plug in your axial torsion, let's say, product into a TEDS ready instrument, and it'll automatically set up, and then you could change it to a different one, a different load cell, and the instrument would automatically set up with that. Also, we can provide you with some wireless solutions. So we have a full line of wireless products, and sometimes running wires throughout your plant or through your operation can be cumbersome and hard to manage. And our wireless product will work with all of this product we showed you today, and reduce the amount of wires and setup in your factories. And then lastly, we've got a large offering now of digital products. And so a lot of companies are doing things with Ethernet.
Multiple people are now exiting.
And Profibus and those things. And we have instrumentation that can connect your multi-axis products directly to your networks. Now I'd like to turn it over to Keith, who's going to tell you a bit about some applications and use cases.
Hello, everyone. Thank you for attending. Thank you, Ken. Applications, these are just to plant a seed. You know, these are fairly basic ideas, but wind tunnel is one that comes up fairly frequently with us. There are very complicated load cells called wind tunnel balances that are used in wind tunnels. But for a basic setup, a 6-axis sensor can be useful. You can measure lift and drag and yaw and, you know, the various components in the wind tunnel with a single sensor mounted. You may potentially underneath the test article. We have a specific version that has the ability to withstand large moments, but measure relatively low forces. And that's the kind of loading condition you end up with when you have a test article in an airstream or wind stream where the sensor is down, say, fairly far below it. So you have a large lever arm. And so large moments, you don't necessarily care about those moments, but you want the load cell to survive. You don't want to size the sensor up so high that it can take the moments and then lose resolution on the axes of interest. So that's somewhat interesting. Aerospace structural and fatigue testing, and that really goes for any structural fatigue testing. You're making assumptions. You may make assumptions that the loading is purely axial. You may be right, you may be not. Our low profile load cells are very good at rejecting errors due to the eccentricity of load, but your test specimen reacts differently, certainly, if there's bending involved. And so a 6-axis or a multi-axis sensor can tell you what those loads are, and then you can either adjust a test to minimize them, or you may just take them into account. If you're doing, say, testing on multiple test articles, you'd want to make sure that the bending and the extraneous loading is the same between the tests, so you can get apples to apples comparison. And that goes when you're doing, say, computer model validation. If you're feeding data in, you're making assumptions about the end point, the constraints. If they're incorrect, then you may be feeding incorrect information back into the simulation. As you say, garbage in, garbage out. So you're trying to fine tune a model and validate it. It's good to know if some of your assumptions are correct, or if all of them are correct. Friction testing. We've got a number of customers who do various methods of rheometry, measuring friction with spinning discs or rotating elements. A spinning disc, you could use an axial torsion load cell. If you're going to, say, press down on the surface and then slide across the surface, one of our 3-axis sensors could be used with just the FC and, say, the FX or FY. It's also useful to have the extra axes then to know if you're not oriented properly. You might see that you're actually getting a lot more F, say, Y than you expect, and that either means you've got a problem with the test, or maybe your test article likes to squirm around a bit on the test surface. So it's definitely interesting to have the extra information, although a typical test would really only measure, say, normal load and then one shear. Moving on. Medical device testing is very commonly uses multi-axis sensors or multiple sensors in configuration so that you can measure multiple axes. The advantage of an actual multi-axis sensor is a lot more compact package than trying to come up with some combination of multiple load cells to do the same thing. you can imagine ball joint or any kind of a medical prosthetic has a relatively complex range of motions. Typically, you never just one axis of force. And so, say you're measuring the wear characteristics of a socket, you'd really want to understand what the forces are, and then be able to duplicate those in some kind of a long-term test so that you can study, say, the differences between different materials and whatnot. But obviously, if your test conditions aren't the same between different types of specimens, and really you don't know what was, say, causing earlier wear out on one versus the other, if you don't know for sure the loading conditions were the same. Robots, interesting application. There's lots of things being done these days with robots, robotic arms. Multi-axis sensors can go at the end of an arm and can be used to measure either weight or forces applied during an operation. They can also be used for, say, collision detection. If an arm is moving around, you'd certainly want to know if it's getting ready to impact something. Robots are very good at very precise measurement, but they're not necessarily that good at knowing where they are. So if you're trying to come into contact with a test or an item or an object, force feedback can help make sure the robot doesn't, say, move too far and come into contact if you're not expecting that. Moving on. Hydrofoil, this is an interesting application we actually did with the Navy, where they're studying the effects of a hydrofoil in a wave tank. And we had some 3-axis sensors used, and they basically measured the lift as the the boat moves through the water. It starts to rise up on the hydrofoils, and that creates, say, an FZ load or an FX load in this case. And then they also want to know how much drag, and obviously the relation between, say, speed, drag, and lift was something that was interesting to them. And these were water-resistant versions of the sensor that were actually allowed, to be submerged and survived quite well. They do have to be specially treated for that, though, so not just a standard product. Seat testing is pretty interesting. You can imagine this is a pretty basic drawing of one, but there are somewhat complicated fixtures that are used to press against a seat. But you imagine if you're trying to validate or evaluate different seat designs, it really makes a difference how the fixture interfaces with the test article, especially as the test article wears. So you imagine in this example, you can see if you were pressing right against that seat and it had that, say, feature right there in front of the fixture, as that starts to wear, you could imagine the load application point actually moves from being, say, on center to trying to create a bending moment. That can be bad for the sensors, also creates errors, also creates situations where when you test, maybe the seat fails earlier than expected to, but it really turns out the lever arm of your force application down
Joe DeVito
was
is now joining.
Wasn't what you expected. So then the next test, maybe with a different seat back, the hinge lasts longer, but it's really because you were applying less of a lever arm and you didn't realize it because the foam, say, wore more quickly or the shape was slightly different. So very interesting to measure. And then, once you know what's going on, you can either redesign the test such that it, say, minimizes bending, or, try to make sure that the characteristics are the same when you run a different specimen to, apples to apples comparisons. Center of gravity, lots of systems, you say multiple load cells. Say if you want to measure the center of gravity
Joe DeVito
plane.
Is now exiting.
You would have a system where you might have, say, 3 or 4 load cells beneath the surface, and then you could measure the CG within that. With a single multi-axis sensor approach, you can also do something similar, but it's can be done with more complicated geometry and done in multiple axes. Moving on. This is somewhat interesting, is that you can make a plate system with multiple, either single axis load cells or multiple multi-axis load cells, and create quite a large system that can be used to measure loads, whereas you might have difficulty, say, finding a single 6-axis sensor that was large enough to survive very large reaction loads due to, say, a big platform. You can actually mount multiple 3-axis load cells at the corners and have quite a big platform. For example, you have a machine sitting on this base, say, or a robot. If you want to know if the robot arm contacts something and starts to create a tip over, you could do that, where a sensor at the very end of the arm only can tell you if the end of the arm is touching something. But if, say, the middle of the arm, right, there's no force feedback there, but a plate system like this could allow you to sense that and recognize it. Also, lots of different analysis situations where you have a reaction load, where you have a fairly, say, large footprint. Something like this can be useful. Moving on, frequently asked questions. One that comes up fairly regularly with the 6-axis is, do I need to use a BX8? And the answer is you don't need to, but we highly recommend it. And we say that especially after we've worked with a number of customers who did not use one and are trying to do the instrumentation themselves. It's not that complicated, but in reality, it does complicate things pretty dramatically. All axes have to be sampled simultaneously, and then their math performed to understand the actual axis outputs. The BX8 does that. Also, we do have software that comes with it that allows you to do the visualization, data logging, and all that. But one of the neat things about the BX8 is you can set it up using software, and then you can disconnect the software, and it just sits there as a black box. But it runs the calculations internally and scales its own analog outputs. So instead of having 6 signals that you have to deal with and figure out, what the actual axis loads are, the output from the VX8 is just, say, plus or minus 10 volts equals, FX, FY, FC. So it turns it into 6 discrete sensors, essentially. The BSC4 is a 4-channel box that we use with our 3-axis sensors. That's not as necessary because the 3-axis sensor is 3 discrete axes, basically, but it certainly simplifies things. You plug into one little box and you get your outputs from the box, either as amplified voltages or as a USB connection to a PC. Another thing that comes up fairly commonly is, what if I need only 4 axes or 5 or 3? Well, it depends. We may have a lower axis count sensor that has the particular combination of axes you need, or we may not. But a 6-axis sensor can measure all of the axes, and you don't have to use all of the data if you don't want to. But you do always need the 6 channels, because the way they work, you can't get only 4 axes without still measuring all 6 channels of the sensor. So again, once you have the data too, you might find that you are interested in it. You assume that there's, say, nothing going on in the FY axis. Well, once you start taking measurements, you might find there's a little more there than you expected. And then either you change your test setup to eliminate it, or you just, it's there and you can use that information appropriately. Next, do we offer customization? Absolutely. We do special configurations and calibrations. OEM special products, such as for robotics or medical applications. Special calibrations are pretty interesting because the sensors are always optimized for, say, the most broad use case allowed. And so in a 6-axis sensor, you've got 6 axes. They're all rated for, plus or minus a certain Newton meters or, force or a torque value in each axis. But in a lot of cases, you may say that, I'm only using the sensor down at you say in compression only in the FC, and then I have small moment loads, and I have a large FY load, for example. And if you do know those conditions, you don't have to know them exactly, but okay, you're not going to be, applying any tension load, for example. Well, we can optimize the calibration such that it fine-tunes the performance under those loading conditions. Now maybe it doesn't work as well if you use it in the other direction, but we can kind of move the calibration such that it optimizes it in your use case. How do we best engage an application expert? Well, a phone call or an email is nice. What we like to do, though, is start to talk about the geometry when you're talking about multi-axes. And so a sketch is always very useful. A lot of times it's proprietary, so you may not want to provide all of the details. But what we want or need is something quite basic, but where's the load cell? Where's the test article? What's the geometry, the distances, approximately applied loads, those kind of things. We can start to understand, make sure we get a large enough sensor to survive the measurements, and also, a small enough one to have enough resolution for those same measurements. Next, please.
All right, so we're going to have a Q&A opportunity here. So if you have a question, you can unmute your mic, and as well, you can also use the chat window. And in fact, we've got a couple already for our team. First of all, Bill wants to know what's the time lag on the BX8 if you're feeding it into another DAC? Anybody got a recommendation on that?
Oh, it's pretty fast. It's like 4 kilohertz, something like that. The sample rate is, say, 48,000 samples per second synchronous. When you start running the math on the coefficient matrix, so it knocks it down a bit. I think the limit is about 4 kilohertz for the bandwidth pass through once you have all 6 axes and the calculations running.
I more meant the time offset. Because was it the BX8 or was it a different model that I can feed into like a SOMAT, for instance? And I was wondering, all the data coming in from accelerometers, I would want it to be as in sync as possible with the load cell results.
Well, it's if you're talking about digital data, it's all packetized and the data is synchronized. So everything coming out of the BX, all data packages include synchronous data. So if it's sampling them all, say in the same channels, they're all synchronized in the data packet.
Yeah, so I think the question is, how long does it take to do the computing? That's a good question. Is this Bill?
Yes.
All right. We'll look into it and get you an answer.
That'd be great. Thanks.
Sure.
Mike wants to know, does the BX8 provide the excitation to the sensors?
Absolutely.
And then we've got another question. For a 6-axis sensor, is the calibration done axis by axis or by or all axes simultaneously?
Multiple axes simultaneously. So there'd be a force at an offset applied, which creates a combination of loads. So there's multiple combinations of loads applied during calibration.
And he's got another specific question. In which cases do you have a 72 figures compensation matrix only on a 6-axis sensor with a double bridge? Is that true?
That is true, but it's not truly a double bridge. It's 12 bridges, and you're basically running a more complicated matrix calculation, but it's not. It's basically an extra bridge per bridge to help error correction of the crosstalk. There's not like a dual bridge load cell is like 2 redundant signals. With 12 bridge 6-axis, it's still a 6-axis. You get one single result for any axis calculation, but there's a correction or a tuning or an improvement in the calculation is done by having a second bridge for each, say, channel calculation.
We've got one from Derek. Is it possible, or has someone successfully connected a 3-axis unit to an Arduino? I don't know if I pronounced that right, Arduino?
Arduino.
Yes, it is possible. Especially the 3-axis, it's just like 3 load cells. So if you can connect a single load cell to an Arduino, you can connect a 3-axis. You would need an amplifier typically between it and the Arduino. And most Arduinos have fairly low resolution on their analog to digital converter. So you may, want something that improves that resolution, including an Arduino-based add-on A to D converter. But we have a lot of customers who are doing that these days.
Yeah, I would just add, use caution in the bridge amplifiers. These are ratiometric sensors, so any noise that may come through on the supply side will impact the signal. So quality of instrumentation is really important.
That's great. Mark wants to know on the plate design, what is the largest amount it can handle in MX?
Well, typically these would be based on our 3A series 3-axis sensors. So the largest, say, X or Y load would be basically sort of 4 times the largest capacity minus some safety factor. So maybe divided by 4 again, just to make sure you're well within the working range of the load cells. Ken Bishop could probably answer. I can't remember what the largest capacity.
I think it's 500 kilonewton or 500 kilonewton.
So about 100,000 pounds ish. And you could say, okay, it's 400,000 because there's 4 sensors, but you'd want to back off of that for safety factor. So the advantage really is that you can start to, allow very large moments because you have a large plate, and then the reaction points, are out off the center line by, as much as you need. So you start to react very large moments without killing the sensors.
Good point. Ron wants to know, using a BSC4DC with a 3-axis cell, can you send a command via VB to retrieve all 3 axis values?
For the BSC4?
Yeah, the BSC4DC.
No, I think it'll just stream the data, but you will get a single packet. But it doesn't store them until you ask for it. You can send a command that says read, and it'll send back a packet which has the 3 axes data in it, but it doesn't accumulate them until you ask for it, and then it'll send you out multiple readings.
Okay. And Ron, if you need more information on that, be sure to contact our technical team. Charles wants to know, regarding application of multi-axis 6-sensor application for underwater object hitting stones, what is high-speed capability for dynamic strike applications for strain gauge load cells? Is there another kind that can do or handle high impact loads?
Very good question. And as they say, the devil's in the details. But these are very stiff. All of our multi-axis sensors are quite stiff, which means they react to impacts as well as any of our sensors do. And many customers do use our, say, low-profile load cells and others in impact testing. That said, impacts can create large loading, conditions, and so you have to be careful of the survivability of the sensor, and also, there's a limit. They can only react so fast, but it's down in the millisecond range, typically.
That's great. We don't have any more questions coming in the chat. Is there anything else you guys think would be useful in sharing today that from these questions?
No, I just hope we shed some light to going back, taking a look at your applications, rethinking how you're doing existing testing as well, and give multi-axis a shot on future applications. The accuracy is getting very good, and there's usually a place you can find to integrate these that will really complete the test picture.
And just for resources, we do have online on our website brochures, our catalog, data sheets for every model, so that as you begin to design any test requirements, you can look at the specifications. And we've got some videos on setups on our YouTube channel, and a lot of app notes. You saw some of the diagrams there, but we give you more detail on what the specific products were used, and sometimes that can spark an idea or a question. But our application engineers and technical library are here to assist, so be sure to reach out to us if you're evaluating use or have questions like what we just answered for some of the people that are currently using products. With that, I want to thank everyone for taking the time to join us today. We'll be posting this online on our YouTube channel and also sharing it to all participants, but we'll be scheduling our next event on our Axial TQ product, and that will be scheduled in July, so hopefully we'll see you there. Thanks so much, everyone, and hope you have a great day.